So everybody say hi, Grant.
Hi, Grant.
All right, we're going to be talking conservation of energy today, and I want to do a review of everything that we've done so far, just so that it's all clear in your minds. Our big concept was work, and work is done by a force over a distance. And so we write work equals force times distance parallel, which is equal to force times the distance times the cosine of the angle between the force and the distance. And what we discovered was that when we do work on an object, the work that we do changes the kinetic energy of the object. So that if we add up the net work done by all forces on the object, that net work is equal to the change in kinetic energy of the object, or 1/2 mv final squared minus 1/2 mv initial squared. Please note that we're talking about the total work done by all forces. And along the way, we had a couple of principles to help us compute work. For example, if a force is pointing in a particular direction and it moves a distance in the same direction, then the angle between these two is 0 and the cosine of 0 degrees is 1, so that the work done would simply be force times distance. And if a force is pointing in a particular direction and the object moves in a direction opposite to that force, then the angle between the two is 180 degrees, and the cosine of 180 degrees is -1, so that work is equal to negative force times distance, because the force and direction are in opposite directions. Force and distance are in opposite directions. And if the force is in a particular direction, and the object moves perpendicular to that direction, then the work done is 0. Because the angle between the two is 90 degrees, and the cosine of 90 degrees is 0. And so our principle is that perpendicular forces never do any work. Forces perpendicular to the direction of motion never do any work. And we also computed the amount of work done for a couple of special forces. And the first one of those was gravity. So that if gravity is doing work on an object, then gravity pulls straight down, and if the object has a delta H that is positive, then the work done by gravity is going to be negative mg times delta H, because gravity is pulling down and delta H is going up. And yesterday, when we computed the amount of work done by a spring, what we found was that we could not use this formula exactly because my force is continually changing. F equals negative kx. And so because of that, we had to draw a graph of the force and compute the area. And when we did that, we found that the work done by the spring was negative 1/2 kx squared. And that's what I stretch from x equals 0 to x equals x1. So far, so good? All of this should be familiar to you. Yesterday, we talked about the idea of storing up energy, or conservation, or potential energy. Okay, let me talk about potential energy then. We said that if a force is a conservative force, that is, if it stores up energy instead of wasting it as heat, then the amount of potential energy that it stores up, the change in potential energy of the object that it acts on, will be the opposite of the work done by that force. So that, for example, for gravity, we can take our formula for the work and say that delta U for gravity is equal to mg times delta H. And delta U for a spring is going to be 1/2 kx squared when I move from 0 out to x. How are we doing so far? And you guys did some homework problems based on this. How did the homework go? Perfectly fine? Yep. Kind of formula plug in solve sort of thing. All right. Today, what we're going to do is put it all together. But before I do that, I want to talk just a little bit more about the idea of conservative forces to help you have some good intuitions about conservative forces. One of the cool things about conservative forces that you can prove with calculus is this. Conservative forces have the nifty property that when they do work on an object, that work is path independent. And what I mean by path independent is this. Let's say that I have an object that is going from point A to point B, and it is going to be acted on by a conservative force. And we don't know or care what that is. Maybe it's gravity. I mean, you can use gravity in your mind as an example of this. Then, if I go from A to B like this, that's one path. If I go from A to B like this, that's another path. And if I go from A to B like this, that's another path. Conservative forces are going to not care about the path. The only thing that is going to determine the amount of work done is the difference in position between A and B. So that the work done is the same for all paths from A to B. I could even do a really crazy path like this. And the work done would still be exactly the same as the path straight across for a conservative force. Now here's why this matters. Check this out. Suppose I have a roller coaster. And my roller coaster really does look like this. And I want to know how much work is done as the coaster falls. How much work is done by gravity as the coaster falls from here all the way down to here? And the answer is, it does not matter what the path is, because gravity is a conservative force. The work done by gravity is equal to negative mg delta h. And since my delta h is 0 minus h, the work done is going to be equal to mgh. In other words, the exact same amount of work is done by gravity as if the coaster just dropped. Because work is path independent. Does this make some sense to people? What that does for us is it allows us to simplify complicated problems. Yes?
So work is path independent for all forces or just for gravity?
Just for forces that are conservative. Right. Now the problem is we don't necessarily know which forces are conservative, so let me give you an idea of some forces that we count. The big three that we're going to encounter, examples of conservative forces. are going to be gravity, certainly. Are going to be springs, spring force. These are our biggest two so far. Later, the electrical force is going to be a conservative force. And examples of non-conservative forces are going to be friction and air resistance. Any force that creates heat in its operation is wasting some energy, it's not storing it up. So when you have an object that slides by friction across the floor and it comes to a stop, then the bottom of that object gets hot because of the frictional force. All the kinetic energy of that object has gone into heating up the object, and it's thrown away. I say it's thrown away. You could actually take some of that heat and turn it back into useful work, but only a fraction of it. Yes, sir.
So where does that leave normal and tension?
Interestingly, a normal force is going to be a force that is perpendicular to the surface, but it's not always perpendicular to the direction of motion. So, in this case, my normal force is actually doing useful work, but in this case, it's not. So, you would have to know what is causing that normal force in order to make a determination. In this particular case, my normal force is constant, and a constant force is always conservative. Okay, that gives us the lay of the land. Now, what we want to do is just take all these pieces and we want to put them together to make an obvious observation. Let's say I have an object. And here's my object, and we are going to act on it with several forces that are conservative. So our setup is, if an object, not any object, if an object is acted on by conservative forces, and let's have some here, F1 and F2 and F3. Right, so we've got conservative forces acting on it. And then, what can we say about the work done by all of those forces? Let's take a look at the net work done by all of those forces. Well, that's going to be the work done by force 1, plus the work done by force 2, plus the work done by force 3. And if I have more forces, it would be all the way out to however many forces I've got. Now, I know two different things about the work done by all these forces. The first thing I know is that the net work is equal to the change in the kinetic energy of the object. That's the work energy theorem right there. And the second thing that I know is that the work done by each one of these conservative forces is the opposite of the change in potential energy in the object that results from those forces. So that the work done by force number 1 is the opposite of the change in potential energy for force 1, plus the opposite of the change in potential energy for force 2, plus the opposite of change in potential energy for force 3, plus all the way down the line to the opposite of, we just drew the minus signs, the opposite of change in potential energy for the last force. And that is equal to the change in kinetic energy of the object. And if I now take and wrap up all of these changes in potential energy as the total change in potential energy, delta U total, then what I find is that the total change in potential energy is equal but opposite to the change in kinetic energy for the object. Now, this was just simple substitution, right? But it actually is a profound, profound idea. Look at what it's saying. If an object is acted on by only conservative forces, then all of the potential energy that we lose becomes a gain in kinetic energy. And all of the potential energy that we gain becomes a loss in kinetic energy. In other words, potential energy and kinetic energy will not be lost, but they will be traded back and forth between each other. You can think of them as like two separate bank accounts that trade money back and forth, but the total remains the same. In fact, we can take this same expression right here and add delta U to both sides and get this expression right here. That the total change in kinetic plus the total change in potential adds up to 0. Or in other words, the change in the quantity kinetic plus potential is equal to 0, which implies, therefore, that kinetic plus potential will be constant and not changing. Now, what does this mean? This means that we can identify the quantity K plus U as the total energy of the system, and as long as only conservative forces act on my system, I'm not going to lose any energy. I'm just going to trade it back and forth between kinetic and potential. The only way I can lose or gain energy is to have it pumped in by or taken away by non-conservative forces. So we're going to define a new quantity called the total mechanical energy. E is equal to K plus U, and the total mechanical energy of the system is going to be a constant as long as all forces are conservative. Now, that's the theory. Let me show you how easy this is to use in practice. You're going to love conservation of energy because it makes problem solving really, really easy in a wide variety of circumstances. Let me know when you're ready. Okay, almost there. Okay. Let's consider a question that we answered before. An object is thrown with speed 10 meters per second from the top of a 30-meter building how fast is it going when it hits the ground? Now, of course, we want to draw ourselves a picture. And here we've got y equals 0 down at the bottom, and y equals 30 up at the top. And now we've got our object. One of the interesting things about the object is we're not told the mass of the object. We know what to do with that. What are we going to do? Well, we hope it's gonna cancel out, but until then, we're gonna call it M, right. So here's my object, mass M. Here's another thing that's interesting. We're not told in what direction it is thrown. Interesting. So I don't even really know how to draw it. I'm gonna just give it initial velocity in that direction, because I don't know. I'm gonna have it hit the ground right here. Guess what? Because work done by gravity is path independent, it doesn't matter which direction I throw it. The answer will be the same for every possible initial direction. Whether I throw it straight down off the building, or straight up, or upwards, or whatever, the speed will be the same no matter what. Because work done by gravity is path independent. How cool is that? So, now, what we're going to do, the spirit of conservation of energy, is that we're going to pick a point where we know the total mechanical energy of the object. And then we're going to use that, transfer that total mechanical energy over to the point that we're interested in. The point we're interested in is y equals 0, here on the ground. And the point that we know is the initial point right here at y equals 30. So, first of all, let's calculate the total mechanical energy at y equals 30. And the total mechanical energy is going to be the sum of the kinetic energy plus the potential energy for all of the forces acting on the object. How many forces are acting on the object? Just one, gravity. The object is in, what do we call that? Free fall. Yeah. So at y equals 30, we have k is equal to 1/2 mv squared. And we can do this in our heads. It's going 10 meters per second, so v squared will be 100 times a half is 50 times an unknown m is 50m. And u, gravity, is equal to mgh, and mgh is equal to m times 10, times g is 10 meters per second squared, times 30 meters is equal to 300 m. See how these computations are nice and easy? And the K and the U together represent the total energy that the ball has as it's leaving that building. So I can label this as E, the total mechanical energy, is going to be 50m plus 300m is 350m. Just like that. And that's at y equals 30. Now, down here on the ground at y equals 0, my kinetic energy is once again 1/2 mv squared, but this time I do not know what the speed is. In fact, the question is asking me, what is the speed? So I'm just going to have to leave that as v. But I do know the potential energy due to gravity because I'm on the ground. And because I'm on the ground, automatically, what's my potential energy? 0, because I'm at the 0 point. If you chose your 0 point up here, by the way, then this term would be 0, this term would be negative 300m, but in the end, you would get the same answer. So you can choose your 0 point wherever is easiest for you. So that the total mechanical energy here is 1/2 mv squared plus nothing. This is what we call energy accounting. You simply go through and you add up kinetic plus potential for every force, and that's it. That's your total amount of energy. And we use the word accounting. Accounting makes you think of what? Money. And we're thinking of energy like money. So here is our energy accounting. And now for the big moment. We've done energy accounting at this point and at this point, and we are now ready to use the principle of conservation of energy by saying that energy is constant, which means that if I have accounted for energy at any point, the total energy here, the total energy here have to be the same number, which means that 350m from the top has to equal 1/2 mv squared on the bottom. Look at that, the masses cancel out. And that gives me, Deanna's got the right idea, and all of you should be grabbing the calculator and calculating that speed. And if I've done my math right, I think it's 26 meters per second. Is that correct?
26.5. Close enough.
That is a lot easier than components and sines and cosines and all the stuff that we did way back in chapter 3. In fact, once you get used to it, you can actually do these kinds of computations in your head. You can imagine doing this stuff in your head and adding it up and setting it equal, and you have one single equation, and you're good to go. Sometimes people like to organize their work. Accountants like to organize their work. And when they do, they organize it into spreadsheets. And so some students like to do all these computations right here in a sort of spreadsheet, or what we call an energy chart. So I'm going to show you how to do an energy chart. If that's helpful for you, you may do it. If it's not helpful for you, you can do it like this. There has to be an energy accounting somehow, but I don't care how you organize your work. So let me show you one way that is helpful for some people. Let's take this same problem right here. I'll copy the problem over to the next page. Move it. And copy. And paste it. Alright. And so an energy chart would look like this. What we would do is to do a before and an after scenario. And sometimes I label them before and after, sometimes I label them explicitly like this. And then we're going to have as columns in our chart the kinetic energy and the potential energy for every single force involved. In this case, it's just gravity. And if you want to write the formulas here to remind yourself, that potential energy is 1/2 mv squared, and that kinetic energy is 1/2 mv squared, and potential for gravity is mgh, then that works too. And now it's just a matter of plugging in values. And when I do this, I get 100 m, excuse me, 50 m. That's 1/2 of 10 meters per second squared times m. And here I get 300 m, mgh. Down at the bottom, I get 1/2 mv squared and 0. Add them up to get the totals. And now, energy before has to equal energy after, and my equation pops right out of the table. 1/2 mv squared equals 350 m. Some people also do these tables sideways, so they have k and u going down, and they've got y equals 0, y equals 30 going across. So I don't really care how you organize it, so long as we have a total accounting of energy at 2 different points, and we set them equal here. Does that make sense to everybody? Cool. Let's work a harder problem. You knew I was going to say this. A 10-gram ball is placed on a vertical string with constant K equals 850 newtons per meter and compressed distance of 2.0 centimeters. Two questions. How fast will the ball be going when it's released? And the second question is, how high will it rise? Energy accounting makes this kind of thing snap. But we do need a picture first, so that we can decide on our 0 point. So here's our picture. We have a ball placed on a spring like so. And here, we are in the equilibrium position, y equals 0. Now we're going to take this and we're going to compress it by 2 centimeters. So that my ball is now down here. When it's down here, this is the first key thing. What is the y value when we've compressed it by 2 centimeters?
-0.02 meters.
Negative 2 centimeters or negative 0.02 meters. Yes, very good. Okay, so we're going to compress it, then we're going to release it, and when we release it, that ball, the spring is going to snap back to its equilibrium position, but the ball is going to go way the heck up here into my problem. And it's going to go up to a height, and I don't know what that height is, but we're going to have to call that h. And so now, to answer these questions, we can do some easy energy accounting to see what is going on. Let's account at y equals 0, y equals negative 0.02, and up there at y equals h. And we'll take a look at the kinetic energy of the ball, at U for gravity, and at U for the spring, and then at the total energy. Now, we have two different times when y is equal to 0. The first time when y is equal to 0, we have the spring compressed, right? But we have another force holding it in place. So that's the force of our hand or whatever's doing the compressing. So that's not a very good test of what's going on in question. The second time is when we release it, then the ball is going to come back up. And right on its way out, it's going to hit y equals 0. And right at that moment, it's going to be going the fastest that it ever goes. So let's analyze it right at this point, y equals 0, when it's going at a high rate of speed upwards. So at that point, it's going to have a speed, and we don't know what that speed is. It's 1/2 mv squared. We know the mass, 10 grams, or 0.01 kilograms. So our kinetic energy then is going to be 0.005 v squared, 1/2 mv squared. And because this is the chosen 0 point, automatically my potential energy for gravity is 0, my potential energy for the spring is 0, and all that I have, energy-wise, at that point is a kinetic energy of 0.005 v squared. What about at negative 0.02 centimeters? Well, right at negative 0.02 centimeters, right when I take the hand away, I have no kinetic energy. My ball is very briefly stopped. I have a little bit of negative potential energy because I'm below ground, right? So that's going to be negative mgh, or negative, let's see here. 0.02 times 10 is 0.2. Let's put all the factors in here. It's going to be m is 0.01 kilograms times g is 10 times h is negative 0.02. gravitational potential energy. Yes?
Isn't it positive because it's negative MGH, and since H is negative, 2, you just get positive?
Okay, careful. So the work done by gravity is negative mgh, right?
Yeah.
The potential energy for gravity is therefore the opposite of that, which is positive mgh. Think about it like this. Use your gut on these. If I have an object that's at a positive height up here, it's going to have positive potential energy. What about for the spring? Well, for the spring, I'm going to have potential energy. Sometimes my chart gets a little messy. 1/2 kx squared. And my K is 850 newtons per meter. Is that right? And my X is 0.02 meters squared. So that when I run the numbers on that, I get 0.17 joules. Got a question? Sure. Okay? Good. And now when I add all of these up, what I get, the total energy that I get is going to be the 0.17 plus the negative 0.002, which is 0.168 joules worth of energy. Notice that we got an actual number here. We like this because it indicates to us that we actually know the amount of energy that's in the system. It's 0.168 joules. So this is a happy thing. And then finally, up at y equals h, oop, I did not mean to do that. You down, you up. Finally, at y equals h, notice that the ball is going to go up to its highest height. Right at the top, what is its speed? 0, which means it has 0 kinetic energy also. So we can say at the top that it has 0 kinetic energy. It's going to have a potential energy of mgh, which is equal to 0.01 kilograms times 10 meters per second squared times h, or 0.1 h. And the potential energy for the spring, be careful here, students will often dwarf this one up. It is true that the ball is up here at height h, but how much is the spring stretched by? Nothing. That's right. The spring relaxes as soon as the ball leaves it. And so the spring has no energy stored up in it. Does that make sense? So be careful, because I'll have a lot of students that will try to put in that height h into the spring potential energy and discover the spring has huge amounts of potential energy when it doesn't. So we have 0 potential energy in the spring, and therefore the total energy up at the top is just 0.1 h. Well, that's my energy accounting. Does it make sense to everybody? Any questions about it? Now we're ready to use, yes ma'am?
The problem says the constant is K equals 850. Why in the column K is there not constant?
Thank you. Thank you. I'm so glad you asked that question. We have an unfortunate thing going on, and that is we have 2 different things that are called K. One of them is the spring constant that is a little k. Little k like that. And it is the constant that is involved in all of the spring equations. F equals negative kx, and u for the spring is 1/2 kx squared. Separately from that, entirely separately from that, we have also the kinetic energy of the object, capital K equals 1/2 mv squared. Maybe because of that confusion, your book uses Ke for kinetic energy instead of just K. and uses PE for potential energy. And if you want to do that to keep your head straight, that's fine. All the cool physicists do this, but I can see where there's confusion. K is for confusing. So you actually have two different K's here, little k and big K. And in the chart for our energy, this is supposed to be a big K, but it was ambiguously drawn. Better? Good, thank you, that was a great question. So now we're ready to use conservation of energy on our energy accounting chart, and we can set all of these guys equal to each other. So we have 0.005 h squared from the first line is equal to 0.168 joules for the second line is equal to 0.1 h in the third line. And because they are all equal to each other, we can take any two of them, set them equal, and solve. Yes?
Is it B squared for the first one?
It is b squared, thank you. Good, much better. So I can now take, for example, these two, set them equal, and when I do, I can divide both sides by 0.1 and find out that h is equal to 1.68 meters above the 0 point. Boom. Or I can take the 0.005 b squared and set that equal to 0.168 joules, and I can solve for v. Everybody do that this time.
I get 5.8.
Mhm. 5.8 meters per second. Roughly, how fast is that in miles per hour? Your number is 2.2. So if we take that to be 6, right? And you're going to multiply it roughly by 2, so that'd be 12, and then add 10%, that'd be about 13 miles an hour. Does that seem reasonable here for a ball being launched by a spring? That would come off at about 13 miles an hour and go up to a height of about 1.6 meters. Yeah, actually, that's about right. Okay. How are we doing? Good. We're going to do some more conservation tomorrow. And then on Friday, your quiz is going to concern itself with figuring out working energy and conservation. Big players are going to be grabbing in springs.